Continuity. Something to take into account when talking about continuity is that it involves non-stopping. It involves something that doesn't stop, doesn't halt, doesn't fluctuates, just something continuous, basically. I know that's a very abstract definition of something continuous because it can apply to a wide range of scenarios, but this is why I'm gonna use visualizations to explain what continuity is in calculus. So a continuous function can be described, this is a continuous function, regardless of the numbers or the function itself. This is a continuous function. So when a continuous function, which by the way is something that you strive for, something continuous, something where you can empirically use empirical evidence to base your intuition on, or to base your results, your data on. You always want to strive for something continuous, like this. Of course, a continuous function might look like this. You know, it doesn't necessarily has to be positive, always pointing to the positive direction. It just has to be non-stop in it. This, let me explain what is not a continuous function. So this is not a continuous function. So you might ask, what is this open hole right here? Well, that's when f of c is undefined. So at this point of the function, the letter c, so the value c, will not be defined, will not exist. Basically, will break the law of, well, we'll get to that topic later, but basically for now, for calculus, we cannot have a value of c if it's open in a function. So what you're looking for here is a function that is continuous at the value c. You want to basically check the status of that value c. So there's a theorem. A function is continuous if it meets these three criteria. And sorry, let me rephrase that. But a function is continuous at x equals c if it meets this criteria. C, basically, c has to be defined. So x equals c has to be defined. That means that when inputting the value of c into the function, that is, it has to be a defined number. It cannot be undefined or non-existent. The second requirement, b, is that the limit x approaches c, f of x, has to exist. Now, if you recall from the prior video, a limit exists when you can approach a number from the left, a number from the right, and equals this number, when the f of c equals the number. So basically the limit exists if let's say this is a, right? A limit exists at a point c if the limit from the left, so from here, equals L. If the limit from the right, this is this side, equals L, which it does, and if the limit of both sides, let's see, right here, so the limit from the left, which is depicted as a minus, the limit from the right, which is depicted as a plus, and the limit of both sides, so basically this side and this side, equals L. If these three criteria are met, then the limit exists. Okay, so the second criteria for a function to be continuous at c, in this case, let me just erase this, at c, has to exist. Okay, has to exist. And the limit as x approaches c of f of f of the function has to equal that number into the function. So basically, it's basically this criteria. This has to be the same. So let me just illustrate this scenario when a function is continuous. This will be a continuous function. I know it's the same example I used before, but it just meets all of these criteria. So at point C, limit is defined. How do we know that it's defined? Because it's a closed point. I know that's a bad way to explain it, but basically if we plug C into the function, it will give us a number. It will not provide an undefined result. The second one, the limit exists. Like I said, the limit from the left, the limit from the right, it's L, and the limit from both sides exists and equals the same L. So that's defined as well. That's approved as well. Last, the limit as x approaches C of f has to equal C, which is what happened in the first step. So let me just explain when a function will not be continuous. There are 4 types of discontinuity. Well, 4 types of discontinuity of a function at the value of x equals C. I will explain why I emphasize that part. Well, you will see later why. So here, what happens here? Why this example is not continuous? Because C, x equals C, is not defined. As you can see, it has an open dot there, which means it's undefined. The function of f of x is undefined at C. What happens here is that, let me just explain which rule it violates. Sorry. So as you can see here, at x equals C, so x equals C, the function is defined. Here it's not defined, but here it is. So that checks out. Now, let's see criteria number 2, letter B. The limit exists. So for, like I said, for a limit to exist, it has to approach the left side, the right side, and both sides and be equal, which in this case is not. This is L1. So from the left side, the limit, in this case, f of x as x approaches C, from the left approaches L1. The limit of x as x approaches C from the right equals L2, which, as you can see, they are not the same. So the limit f of x as x approaches C, that means when it doesn't have a symbol here or a sign, it means from both sides. Does not, they are different. So L1, L2, which means does not exist. So we don't pass. The third type of discontinuity is called infinite discontinuity. Sorry, that was messy. Okay, let's start with criteria letter A. X at C, it is defined, which is a close point, so that passed. Let's try B. The limit from the from the left, so the limit of f of x approaches C from the left goes to infinity. The limit of f of x approaches C from the right goes to infinity. Same, right? Well, positive infinity. However, As the limit of both sizes go to infinity, as you might imagine, because they do for both sizes, we cannot say that the limit, that x equal to c is continuous at that point, because it goes to infinity forever. It changes forever. So your value will not stay stable, or will not be stable. So that's why it cannot be counted as continuity if it approaches infinity, because it's not stable. It's not a value, it's just infinity. The last but not least type of discontinuity, it's called removable discontinuity. Okay, so again, let's check the criteria. Ax is defined at c. Check that. The limit exists because from the left, from the right, from both sizes equals the same. Even though it's not defined here, it equals the same. So as you might know, a limit exists despite the value that it approaches, is it defined or not, if the limit from the right and from the left and from both sides are equal, which in this case it is. So that passes as well. However, the third criteria, we said that this exists, right? So the limit as x approaches c exists, as we can see right here. But is that equal to f of c? So let's see. So we know that the limit as x approaches c of x is equal to L. Okay, this is just a number. However, if we plug c in this example, it will not give us, well, okay, let me just rephrase that. If we plug at this point, it will give us undefined because it's an open point. We cannot plug that number because it's undefined. However, that doesn't mean f of c doesn't exist. We see here that c is also this point, but that's not included in the limit from criteria B, which means that it's not continuous. Because first of all, you can see this pretty easy because you can use your eyes to see that no function is approaching this value. It's just outside of the continuous function. Well, this function is not continuous, as we might know, because it doesn't meet this criteria. F of c equals this point, L2, which is not the same as the limit. So the limit as x approaches c, f of x is equals L, which is not equal to L2, which is equals to f of c. Therefore, this does not happen. Those are the 4 types of discontinuity. Now, what about functions within intervals? Well, let's draw one. In the interval of a and b, closed interval, that's a, that's b. So is that function continuous? Well, there's another definition that explains why it is, but this is one criteria for general functions, but for functions that are within an interval, you have another criteria. The first part, oh, let me just do it this way so you see. The first part is that f, so the function, has to be continuous in a and b, open. That means without including a and b. So is this function continuous without including point a and b? Yes, it is, because it doesn't have any holes, it doesn't have any jumps, it doesn't have any other points between them. So we're good with that criteria. Second criteria is the function has to be continuous from the right of A. Let me explain that. As you can see here, if the limit approaches, so the limit as x approaches A does not exist. Why? Because it can only be A can only be approached from the right. You see? So there is no function here. Therefore, that limit does not exist. However, the limit as x approaches A from the right does exist. Is L, which is an arbitrary number that exists. So that's another criteria. If f is continuous from the right at A, that's another criteria that the function of f of x within the interval A and B exists. And you might know was the third criteria, basically the same, but with B. Well, vice versa. F continuous from the left of B. So again, the limit of x approaches B does not exist because here we don't have any other functions. But from the right, it does exist. So that's another criteria to know that f, the function of f, is continuous in the interval A and B. So those three criteria have to exist in order for us to state that the function of f is continuous within that interval. So let's do, we might say, let's do this. Now, is that function continuous? Well, f has to be continuous in the interval A and B without including an and B, which it is. It passes. F has to be continuous from the left of B, which it does. The limit is L2. We're good. Now here's the problem. Is f continuous from the right at A of A? Let's see. It approaches A, sure, but it does not equal A. And as you can see, so you might say, well, it is approaching the limit, so the limit as x approaches A from the right exists, right? That's L. You're right, it does exist. However, if we know from the prior explanation that for a value c, x equals c to exist, has to meet these three criteria. So let's say c is defined. So let's say now that this becomes equal c, that is defined. We have this, that is met. Here is where things begin to get difficult. So we can know we can know that B is not gonna be met because the limit does not exist. Like we said in the beginning, the limit from the right does not exist because we don't have anything from the right. So that doesn't pass. And C, as you can see, the limit does not exist. And if even if we would only use the limit from the right, which it does exist, the limit from the right at A, which in this case will be C, exists, is that one, but does not equal C from the right, because here this is L3. So let me explain it better. So the limit as x approaches C, this is C, this is C, from the right exists, comes from here, but does not equal f at C from the right, which is L3. Why? Because the limit at x, which is C from the right, equals L, while f at C from the right equals L3. L does not equal L3. Therefore, this criteria is not met at x equals c. Therefore, this function is not continuous. Why? Because f is not continuous from the f is not continuous from the right at a. Why is not continuous from the right at a? Because at a, the function does not meet these two criteria. It doesn't exist because it doesn't have any limits from the left, and the limit as x approaches c from the right does not equals f of c from the right. Last portion I want to show you is that, last thing you have to know is that a function of a polynomial, let's just start. A function of a polynomial is always continuous anywhere regardless of the value. So the function of x that will be continuous anywhere. That will be continuous anywhere. That will be continuous anywhere. So basically, the function of a polynomial will always be continuous anywhere. However, the function of a rational will only be continuous if the denominator is non-zero. So let's say we have this. If the denominator equal to 0, then it's not continuous. However, if g of x is not equal to 0, then it's continuous everywhere, forever, or anywhere. So let's review an example. These are open intervals, that is, the intervals including values within them. So this function of f of x in this interval, it includes the values of 1 and 3. These are closed intervals. F of x do not include the values of 1 and x. So this is 1, this is 2, this is 3. So let's see which of those intervals are continuous and which aren't. If you can see, let's say this open. Let's say letter A. From 1 to 3, is f of x continuous from 1 to 3? No. Why? Well, first, because it does not, as you remember from the theorem of continuous function within intervals, a function is not continuous. A function has to be continuous in closed interval b, a and b, which without including this, is that continuous? It does not, because it includes a jump discontinuity. So no. What about that one? Letter B, continuous. So now it is including 1 and 3. Is that continuous? No. Why not? Because it also includes a jump discontinuity, as you can see here. Now, what about from 1 to 2? Open 1. So including 1 and 2. Is that continuous? Well, from the right at A it is, but from the left at 2 it's not. And as you remember, one of the requirements for a function to be continuous within an interval, b, the limit at x approach from the limit of x approaching b has to exist from the left, which here it doesn't, as you might see. So no. Also, the limit approaches 2 from the right does not equals 2 from the right. That's another reason why it's not continuous. What about D? Closed interval, so without including 1 and 2, is that continuous? It is, because we don't have anything in between. What about E? From 2 to 3. 2 to 3, is that continuous? Even including 2 and 3? It is, because we don't have nothing in between. What about 2 to 3 without including 2 and 3? Same as E, it is.